Okay.
There you go. Good call. Thank you. Uh, yeah, so I'll post it on YouTube. But and if you have any questions, feel free. We can Zoom and I can kind of walk you through it more. All right. So again, you choose a city. I don't care. Don't choose Buffalo because I'm going to do Buffalo. But any city's fine, except Buffalo. And so the next step, this is the easy part, right? You just want to find population data, and it's every decade. And so the census is done, oddly enough, every decade, like on the decade. So you will find data for each of these, at least for any city that is big enough, I guess. So let me stop share and go to my browser portion of screen, share. All right, get rid of you. Okay. So this is, let me make this smaller. This is the Wikipedia article for the demographics of Buffalo, New York. And usually, if you go to the Wikipedia article for any city, big, and again, it has to be big enough, I guess, you'll find a population chart like this. Sometimes it's like, this is, again, it's like a separate page than the Buffalo page. I think if you went to the Buffalo, New York page, it would also have this chart. Just find it somehow. I don't need a reference or anything. And as I said, this comes from census data. So this is the information. So basically, you just write this down for each of the years on this chart. And it's kind of cool, actually. You'll see here that this is the percent, this is the relative change in the population. So if you do find a chart that has this, it kind of makes your life a little easier in the next problem. But I won't assume you have this, right? Anyway, so you copy this data down. I'll just copy the first few. So let's see, 1900, it was this 3, 5, 2, 3, 8, 7. And again, I'm not going to look at your data and fact check it. 5, 2, 3, 7, 1, 5. I just want you to have data. 5, 0, 6, 7, 7, 5. And I'm just going to take a few. 5, 7, 3, 0, 7, 6. And I'll just do the first column maybe. 5, 7, 5. Where am I? 9, 0, 1. And then one more. It's kind of flattening out. 5, 80, 1, 3, 2. All right. So you copy all the data down. And let me go back now. Stop share, share screen, content, share. All right, so I scribbled it down really fast. It's kind of messy. It's okay. But you'll see here, it starts at 300,000 and it steadily increases. It kind of flattens out in these years, right? There's not a whole lot of growth there, but that's okay. As I said, there's no perfect cities. There's nothing wrong with this data. That's fine. All right. Anyway, so you record it, and you would record all this too. And then the next step. So find the absolute relative growth in the population during each decade. So the absolute growth is, again, just like we talked about in class, the absolute growth. So it's literally how many new people were added or taken away, I guess, between 1900 and 1910. And so all you do is you go up to your population data and you subtract off the population in 1900 from the population in 1910. So for instance, I'm going to do 4,23715 minus 352,387.
Do
Right?
we have to show our work in that, or can we just write the number down?
You can just write the number down. Yeah. And so what's interesting here is you might get a negative, right? If your population is decreasing, this absolute growth will be negative. So there's nothing wrong with that. It just means your population is going down, right? For me anyway, let's see. So I get 423,715 minus 532,387. So I get 71,000 and some change. 71328. Right. So that's that. All right. And then it asks for the relative growth. And so the relative growth, again, is just the absolute growth over the initial or the old value. So for the relative growth between 1900 and 1910, I'm going to take the absolute growth, so 71328, and divide it by the population in 1900, the old value. So I'll divide it by 352,387. All right, and it will be a decimal. You can leave it as a decimal, but as we've mentioned, as I mentioned on Tuesday, usually relative growths are more given in decimal or percent form just for the sake of convenience. So I'll list it as percent, but it doesn't matter to me how you list it as long as you know what it is. 71328 divided by 352,387. So it's that thing, and then times 100 to get it as a percent. So it's about, I'll say 20.2%. All right, so we have a 20% growth between 1900 and 1910. So again, what that means is that if you take the growth in that decade, if you took 20% of the population in 1900 and added it on, that's what your growth was. All right. Questions? And so we're just going to repeat that all the way down. I'll just do one more for the sake of doing more than one. So again, so the next decade, 1910, oops, sorry, I'm off. 1910, 1920. The absolute growth, again, is just how many people were added on or taken off from the population in that decade. So I'm going to take the population in 1920 and subtract off the population in 1910. So, and again, it could be negative. Mine is not, but don't be afraid if yours is. So the population in 1920 is this ugly number, 506,775. And I subtract off the population in 1910. So minus 423,715. So I get 86 or 83,000 and some change. 83060. Okay. So that's the absolute. So again, it's positive. So that means that in that decade, 80,000 people, 83,000 were added on to the population of Buffalo, New York. And now, again, for the relative, I take the absolute growth in that decade, so 83,060, and divide it by the population in 1910. So you're always going to divide it by the population at the beginning of that decade. So population 1910 was 423,715. And again, I'll get it as a percent, but if you don't want to, you can leave it as a decimal. 83060 divided by 423,715, and then times 100. So this is 19.6% growth. So it's kind of interesting. The population is growing by about 20% in these first 2 decades, which is pretty good. That's a lot of growth. And you'll see that it kind of levels out. So as I said, you're not really going to find a city that has data that exactly is going to be exponential, generally speaking, just because exponential growth grows so fast that usually natural things like populations just can't sustain that kind of growth for long periods of time. Something happens, right? Anyway, any questions here? Any issues on how to do this? And as I said, you just continue and fill out the chart. You do one for each decade up until 2010. I don't know why I stopped there. I think because I wanted it to be symmetric. All right. And then there's some questions. Are there any odd jumps or unexpected growths or decays? Can you explain them? And so, you know, these are going to be things unexpected. These are going to be things that are kind of outside forces influencing the population. You know, so if I look at this chart here, we have this huge influx of population in between 1900 and 1930. And then in the 30s, 40s, and 50s, it seems to kind of stagnate. It slows down a lot, right? It grows by 2,000 and then 5,000 in these years instead of growing by, 70,000. So something clearly is happening here in the 30s, 40s, and 50s. I don't know what that would be for Buffalo. I mean, Great Depression, World War II, I have no idea. I don't really know what happened that slowed the population growth of Buffalo, New York in those years. But that's what I'm asking you to find out for this part. And you don't need to go and become a historian, but just do some, it could be, you could even just be like the 30s and 40s, there was the Great Depression, World War II, all that jazz. So you could just list maybe that caused it. If you really like history, feel free to do some more research, do some Googling, see, why the population in your city had an unexpected boom or decay, all right? If you're doing like San Francisco, you might find that the population of San Francisco blew up in like the 90s. I don't know if it did, but wasn't there a tech bubble or something, or a lot of .com boom? I don't know. But you might find things like that. So, outside forces influencing the population of your city, that cause big explosions of population or really shrinking population. Okay. So questions about that? This first page at all? All right, let's see. Almost knocked my tea over. Plot your data on the graph. All right, so this is the fun part, loosely speaking. Uh, plot your data on the graph. So if you looked in the PDF, I included some a graph paper here. It looks like that. It's graph paper. And so what I want you to do is plot your data on the graph and draw a line that best fits your data. All right. So I would advise a pencil, but you're gonna go back to your data. This is your data. And I want you to plot the year on the horizontal. And I want you to plot the population on the vertical. Right? So essentially you can think of the year as being, I mean, this is what it usually is too, but the year for us is going to be our independent variable, or like our X or T variable. And then our population is a function of the time. So it's going to go on the vertical, right? Or dependent variable. All right. So, and this part can be a little tricky depending on how you want to lay things out. But let me go to my paper here, and it's kind of hard to get it zoom out enough, but so on the bottom, I'm going to list time in years. So years, right? And you know, in general, you want your data to fit the paper. It doesn't have to, but ideally, my graph won't be like in this tiny little corner. So I have the years 1900 to 2010, right? So that's 1, 2, 3, 4, 5, 6. So I have 12 like points I need to plot on the X around the horizontal. So 12, 1, 2, and how many boxes do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. I have 40 boxes. So
Good to know.
right, if I have 12 things to plot and 40 boxes, if I skip like every 3 boxes, maybe that will kind of fill it. Like, it's not perfect, but you want to just kind of fill the paper as best you can. So what I mean, like I'll put 1900 here, and then 1, 2, 3, and I'll put 1910, 1, 2, 3, 1920, 1, 2, 3, 1930, 1, 2, 3, 1, 2, 3, 1940, and just, you know, try to 1, 2, 3, 1950, and so on and so forth. And just try to fill it as much as you can. Again, that doesn't have to be perfect. I just try not to make it like super teeny in the corner so I can't see what's going on. All right. And also, if you do know how to graph things on a computer, I don't know what program you'd use, but you could do it there too. That would look really pretty, and it would make your life a little easier. But I think, I don't know. I don't get into that much. All right. So you're going to plot the rest of those on here. Next thing you need to do is set up a vertical scheme, right? You need to figure out what each box kind of represents. So basically what I did here was I said every 3 boxes represents a decade. So on the vertical, what is it going to be, right? And you go back to your data. So my population data starts at 352,000. And let me just see, if I go through the rest of it, it goes up. It looks like it peaks in the 50s at just under 600. And then it was a big city back then. And then in 2010, it's like 250,000. So the smallest my population is going to be as far as my data is concerned is around 250,000. And the highest it's going to be is about 600,000. So if I'm setting up my vertical axis units, the lowest I need to be is 250,000. And so, you know, in high school, I remember doing things like this, but they would also often be like, you can put a little break in your graph. So like you can do like a little boop, 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 boop kind of thing. And so the bottom's like kind of 0. And maybe so this would be 0. I'll put a break in it and I'll start at 250,000. And then I need to go to 600,000. So, and you can just play around with it. Again, it doesn't have to be super exact or anything. Make it simple for you to graph. Maybe I'll go up by, I don't know, 25,000? No, it's too little. 50, I'll do 50,000. So I'll do 50 every 2. So let's see. So that's 300, 350, 4. That's really tiny. You see what I mean? Maybe I will do 25 as 2. So 270, 300, 325. That looks a little better. 350, 375, 400. And these are thousands of people. It's still gonna be really tiny, but that's okay, you understand. Try to make it the full page. 325 or 425, 450, 475, 500. Maybe it's not as bad as I thought. 525, 550, 575, 600. It's not too bad. 625 and 650. All right, it's good enough. All right, so I take up like, you know, a good chunk of the page. Yeah. All right, so that makes sense. We're just setting it up so we can plot things. And again, this is the population. Whoa. Someone's chainsawing outside. This is population. Okay. And feel free to use a different graph or grid if you have a different grid paper you want to use for some reason. I don't really care. You don't have to use this one. This is just what I saw. All right, and now we plot. So I go with my population. 1900, it's 350. So I'm going to put a dot there. So 1900 is here. So I go up to 350 and put a dot. All right. Next dot. 1910, 425-ish. So I'll go up to 425-ish. Put a dot just under there. And again, it's not going to be super precise because we're plotting it by hand, but you know, just do the best you can. The next decade is just over 500. So 1920, I go up just over 500. All right. You see what I mean? It's really going up in these first few decades we have. And then 1930, it's 570. So we'll say 575 just about. Right there. All right. Let's see. And then the next decade is just over that. So it only goes up a little bit in the next. And then I have 580. So it's only going up a little bit now. All right. And you would continue. So maybe I'll just finish and just do it from the thing here. Let's see. So 580, 1950, I did that one. Yeah, I'll leave it at that. You just continue plotting the data you have. All right. All right, so questions about this? We're just plotting. All right, maybe I should finish. So I want to draw my line correctly. Let's see. 660, 530. So let's see, I'll just keep moving over 3. So it's like about there. And then the next decade is 460. So I'm moving down. Something like, I don't know, here. Just estimate. And then 1980s, 350. Really fallen. Poor Buffalo. And then 1990, 330. 2000, just under 300. And then just about the same for the rest. All right, something like that. All right. Again, when you're doing this on your own, take your time, make it all pretty and precise as you want. But this is the data for Buffalo, New York. All right. And again, years are on the horizontal, population, mine is in thousands on the vertical. And so this is kind of an example of what I was talking about. It's not a great data, not great data for our kind of project, because it really booms and then it goes down again. And so the point of this is to model this data with either a line or an exponential. And you can kind of see this as neither, but it will work out for us anyway. All right, getting back to the problem. So we've just plotted the data. Now we want to draw a line that fits it. And so as I said, some data will be better than others. If this trend continued, for instance, right? If it kept going up, it would be really easy to put a line. You would just put a line like there and you'd be done. But in our case, our population goes up and it goes down again. And so it makes it really hard to put one line on it that kind of best fits the data. So what you want to do is you want to just kind of estimate, like, and it's really, there's no right or wrong answer for this. I just want to see that you're trying to fit a line to it, and I want to see that you're able to find the equation of that line. So I don't know. It's hard. So like really goes down. Maybe it starts at 350, obviously. Maybe I'll put it like scatter like right through the data. I think that's what I'll do. Again, it's your prerogative how you want to do yours, what you think is the best line. The idea though for a line of best fit is you want a line that's as close to closest to as many points as possible. So like since it's kind of scattered here, I'm putting my line right through it because the idea there is that it's kind of close to half of them. It's very bad. It's a very bad approximation, but it's as close as you're gonna get with a line probably. All right. So, and then you just draw it. So I'll put mine starting here and going maybe through that point. So like, I don't know, like, oh, that's a pencil. There you go, pen, there you go. Maybe like this. And, finish it. I don't have a ruler, which is my problem in life. There you go. Right. So I kind of put a line. And again, there's nothing like exact about this. I'm just guessing where the line of best fit will be. Right? If your data is different, obviously your data will be different, but try to fit it the best you can. Questions about this? All right, and so this is my line. And so that's, where'd it go? We did this now, so we're good here. We plotted our equation, plotted our data, we drew a line. Now we want to find an equation for this line, right? And so this is the part that I want to see and make sure your work is actually correct. So this part is arbitrary. You draw whatever line you want, but finding the equation of the line, you have to actually do it, right? So to find an equation of the line, like we've talked about a couple weeks ago, you want to find 2 points on the line. So you're always going to start, well, I guess you're not always going to start, but I started at 350. So that would be my y-intercept. And then I'll take another point. I'll take this point there. And again, you can fudge it if you want, be as precise as you want, but I just want to see that you're finding the equation of the line. So I'll take these 2 points as my points on the line, like my x naught, y naught, and my x1, y1, all right? So I'll write them all out, and then we'll find the slope, and as I said, the y-intercept is 350. So x naught, y naught, x1, y1. So as I said, x naught, y naught is this point here. So it's going to be 0, 350. What I should note, I'm gonna say that 1900 is 0. I'll number the decades. So I'll say 1900 0, I'll say 1910 is 1, 1920 is 2, and so on and so forth. You don't have to do that if you don't want to. We did an example like this in class where we talked about the numbering and how you can label them. Your indexing can be kind of made up. It can be whatever you like. It just makes it simpler as far as your numbers, your computations will go, but it won't change your answer fundamentally. All right, anyway, so that's why this is 0, because it corresponds to 1900. So note x equals 0 corresponds to 1900. Okay. So that's what that is. All right, and the next point I took was this one here. And let's see, my labeling is junky, but I think it's, 1960 or 70? It's 70. Right, so 1970, and so under my scheme, that's x equals 7. And then the point was, what is it like? I can actually go to my data, can't I? But you can estimate it, and you can go to your data. According to my data, it was 462. Again, I'm rounding a lot. All right. So this is one way of finding it. Again, you can set it up however you like. The other way you could have done it, you could have done x naught, y naught, x1, y1, And you could have said this is 1900, 350, and this is 1970, 462. All right, and then you could have just found the slope like that, and also that would have been fine. It's just purely indexing and labels, right? I'll do it this way though, as I said, because it's simpler. All right. Any questions so far? So I just found my slope. So it's, again, it's y1 minus y naught, x1 minus x naught. Y1 was 462. Y naught was 350. And then it's 7 minus 0. And then you get your calculator. Oops, there we go. And so 462 minus 350 divided by 7 is 16. Oh, it works out really nice. Look at that. That's amazing. All right, 16. All right, and so the very important part to understanding what this means, though, is that you have to understand, like, basically our x is the decades after 1900, right? Like we said x equals 0 was 1900, we said x equals 7 was 1970. And so this number here, as far as your units is concerned, is thousands of people, and then per decade. All right. If you did it this way, your slope would be in the terms of thousands of people per year. Does that make sense? Because if you do it this way, instead of dividing by 7, you'll be dividing by 70. And so your units will be number of people per year. This is number of people per decade. It's the same model essentially, but you're just changing what the variable represents. All right. And again, I'll accept any version you like. If you want to write it like this, if you want to write it like this, if you want to do it a different way, as long as you're finding the equation of the line and you're being clear on what you're doing. All right, so my slope is 16 and we're good. So my equation is y equals 16x plus 350. All right, questions about that? And so this equation will give me this line. So if you want, you can even write it on here. Y equals, you can't really see it, x plus 350. Right? But that's what you want. Right? The next part, according to your linear model, what should the population be in 1955, 1985, and 2015? Right? And so basically, this question is asking you, do you understand how to use your model? And so, as I said, it's very important you understand what your x actually corresponds to when you write up this model. So as I said, my x corresponded to the decades after 1900. Yours, if you did it this way, could also correspond to the years after 1900, or like what the actual year even. So multiple ways to do it. In my model, what I would do is for 1955, so how many decades after 1900 is 1955? And it's 5.5, right? So 1955 is 5.5 decades after 1900. So you do y of 5.5. And so I get 16 times 5.5 plus 350. Right? And so you go to your calculator and you could just compute that. So 16 times 5.5 plus 350. So I get about 348. Is that okay? Is everyone alive?
Mm-hmm.
All right. Again, though, if you set up your line differently, you would plug in a different number. So if I set it up like this, I would literally just plug in 1955 into my x, and that would give me my answer, right? So whatever way you set it up, just make sure you're plugging in correctly. And then maybe I'll just do 1985. So 1985 is 8.5 decades after 1900. So 1985 is 8.5 decades after 1900. So my population in that year would be y of 8.5. And you would plug 8.5 in to get the population in your model. So 16 times 8.5 plus 350. Right? And maybe I'll just do that one again. So 16 times 8.5 plus 350. So 46. Right? And so this is 486,000 people. And this is the same 1,000 people. Right? And then you do the last one. Right? And so your population that you get from your model probably won't be the population that actually existed in those years, because your function is just a model. It's an approximation. As I said, ours is really terrible because the population of buffalo goes up and then down really quick. So it's hard. If your model is really good, you might be right on the point for what the population was in those years. Right? But again, don't feel bad if you're not even close. Right. Now, this is the fun part. As I said, the graphing and the modeling, I think, is the more interesting part of this. Develop an exponential model for your population data and sketched on the graph before. All right. So we did a problem like this in class. And when we did it, I mentioned that it would be useful for this project. So what we're going to do is we're going to go back to here. And the relative growth, you would have computed this column, right? You would have done all the math and just computed all these relative growths and everything. And when you do that, you'll get a bunch of different numbers. And again, some of them might be negative. That's okay. That just means the population went down. But you would do it all. Maybe I'll do one more just to have multiple points of data. So I'll do the next one. So in 30, let's see, 573076 minus, oh, big number, 506,775. So 66301, and then divide that by the population 1920. So 66301, population 1920 is 506775. 506,775 times 200. So I get about 13.1%.
Now, on that one chart you showed us, the relative growth, is that the percentages on the side?
It is, yeah.
Okay. Just to make my life easier.
Yeah, so those are the relative. Here, let me go back. Stop share, and then screen share, portion of screen. So that you won't always, I think maybe, I don't know actually, Wikipedia might always give you these.
Well, I was researching cities and you have to go down pretty far, but everyone I've seen gives you that.
Oh, cool. Yeah, so feel free, if you have that data, feel free to use it. I can't get this, there we go. But yeah, so like let's see, for 1900, I had, or this decade, I had 20.2%, so it's 20.2. This decade, we computed 19.6, and then we just computed 13.1. Yeah, so they're matching up exactly. Anyway, once you have all of those, to find the exponential model, again, there's not one way to do this, but so what you can do is you can say, if all of these growths, if you compute all these and they're all like 15.1%, then you can just take your growth rate to be 15.1%. But you're probably not going to find that. And so what I would do, and this is a really bad way to create a model probably, but I would just average all of these percent growths up and find an average. And that's going to give you a model that's just really in the middle. As I said, it depends on your city, but that's what I would do. I'd just average them all up. So for instance, let me go back to the overhead. So if I average them, and by average, I mean, again, you add all the numbers up and you divide it by how many you did. So if I'm looking at just these 3 years, what I'll do is I'll do 20.2 plus 19.6 plus 13.1 and divide it by 3 because I did 3 numbers. Obviously, when you do all of them, you have 1, 2, 3, 4, 12. I said I'd do 12. So you'll have 12 different sets of numbers that you'll add all together and divide by 12. But again, if you don't want to find the average and you want to play with it a little more, feel free. You can try different percent growths and see if the function you get fits your data, whatever works. All right, so I'll just pretend this is my number, but again, you would want to average all of them up for yourself and find a good rate. All right, so let's go back. And so let me write out my function. So it's exponential, so we know it's going to look like this, right? 1 plus I to the t. And my P naught will be your initial population. So for me, it's, and again, you can do it, I'll do it as 352 or 300, I'll just do 350. But if you want, you can just put the whole population there. You could have, in this problem, you could have written 300,552, wait, you could have written 352,387. That was what I'm trying to say. And then your model would have popped out the exact population instead of in thousands. Again, it doesn't matter. It just depends however you want to set it up. I'll do it like this to make my life simpler. And then my rate, I said, was 17.6. So I'll put 0.176 to the t. All right. And again, this is the average.
So you basically just rounded, right? And just made it shorter in thousands, like referencing thousands. Okay.
Exactly. Yeah. Yeah. So you, again, but however you want to do it is fine. If you want to put the whole number there, that's good. It just is more writing and it's ugly. But this, you know, whatever's fine. And then the average, this is the average of the relative growth column. All right. So that's how I'm getting that 17.6. Again, you can choose and play around with it as much as you like. The idea is that we want to find an exponential function that best fits this data, right? So my 17.6% growth rate, I was only looking at this first little chunk here. Like if you cut it off after here, my model is really just going to look at like that. But as we see, like the data does go down again. So an exponential model really won't fit this very well. Kind of like the line won't fit it very well, which is why I was saying if you find a city that has just growth or just decay, you'll be better off, but it's all good. All right. All right, so questions so far? This is the model I'm going to take. And there we are. And then it says sketched on the graph from before. So this is, it's a little different. So to find, for the line, I plotted the data, right? I drew a line through it, and then I found the equation of that line. For the exponential, what we did, we were doing exactly the opposite. I found the equation, and now I'm going to plot the equation on the graph and then connect the dots, all right? So you have a few options here. If you have a graphing calculator, you can use the table feature in that to help you plot points. If you don't have a graphing calculator, you can just make a table and plot those points and then connect the dots on the graph. So what I mean is that, so if you have a graphing calculator, let me show you that way first. You go to y equals, make sure you have nothing else in there, and then you put your function in. So 350, and then 1.176, all to the x, and then you'll do, oh, what is it, second table? Nope. Wait, second graph, there we go. And it brings up the table. So this is all your x coordinates, this is your y coordinates. And again, you can just do this by hand too. You can make a little table like this, like off to the side here if you want. This is obviously faster. All right, so this is the decades. So 0 is 1900, make the middle of it. 1 is 1910, 2 is 1920, so on and so forth. And y is the population according to this exponential model in that year. All right, so if I want to graph this data, again, assuming I did it by hand or with my calculator, I would go to my table and I would just plot some points. So at 0, it gives 350, which is my starting value. And then at 1, it gives 410. So 1900, again, which corresponds to 1, I go up to 410. And that's like, I don't know, somewhere in here, and put a little dot. Oh, and I should note, make sure you can kind of distinguish between the dots that I'm putting on now and the original data points. So maybe I'll make these like squares or something, just so I don't get confused. All right, and then the next 1920, it tells me it should be 484. So 1920 is 2. I go up and I put a dot around 484. All right, we're doing pretty good so far, right? You'll notice it's really close to those points. But as I said, it's going to completely ignore the rest of the model. At 1930, I go up and it says it's about 470. So I follow it up. Oh, 570, my bad. So it's like right there. And so it's really good, right? Like for these first 4 points, it's almost exactly the population in those years. However, if I go to 4, it says it's 670, which population Buffalo has never been. So in 1940, I go up and it says 670. So that's like, it's like way off the chart now. It's up there, all right? So is really good for these first years because this is exponential growth. Like the data itself is exhibiting exponential growth. However, after 1930, something terrible apparently happens. The population levels off and starts declining rapidly in the following decades. So my model that I made just based on these first few years is really good for those first few years, but after that it's horrible. And if you go to plot the next point, 5, 780 won't even be on this piece of paper probably, right? So exponential models grow really fast. In any case, once you've plotted all the points you can, you then connect the dots. So it will look something like this. All right, and so your exponential model should have a bit of a curve to it, right? But it will, in mine here, it kind of like swoops, it's like, whoosh, it flies up, right? Right, so questions there? So again, these are both horrible models for the population of Buffalo. And it's really just because we're modeling them with linear and exponential and they just won't fit, right? But it's the best we can do.
Did you say you were going to show how to do the table part of that though?
Oh, making this table?
Yeah.
Oh yeah, sure, I can do that too. All right, so to make the table, let's see, where's my other sheet go? Oh, here it is. So our function was this, right? And so to make the table, all you got to do is, I'll do it on a separate sheet of paper, but you can do it wherever you want. So I'll put t, and then I'll make p of t. And so you want to do, we're doing 0 to 11 or 12. I think it's 11 because 2010 would be 11. So we're doing 0 to 11. And so you want to do probably all of those depending. So like in this case, in this specific example, it wouldn't really matter if I went to 11 because 11 is not on my chart. So it wouldn't matter, but just go as far as you want to get a good graph of the function. But then you just do some computations. So 0, 1, 2, 3, 4, 5, and so on and so forth. And then you plug those in. So P of 0, so it's 350 times 1.176 to the 0. And we know that anything to the 0 power is 1. So I don't even need a calculator for this. This 1.176 to the 0 is 1. And so it's just 350 times 1, or 350. Right? And then we keep going. So P of 1 is 350 times 1.176 to the 1. And that we'll need a calculator for. And you can do this on your scientific calculator. Maybe that's what I'll do it on. I have an assortment of calculators apparently. Right. So anything to 1 is itself, so I don't need to put that in. So it's just 350, 350 times 1.176. And I get 411.6. So I got my calculator. It is, okay, good. All right, and then you keep going. So P of 2 is 350 times 1.176 to the 2. And again, on a scientific calculator, I like to do the exponential exponentiation, I like to do this part first. So 1.176 and then caret 2. So I get some number, and then I'll multiply that times 350 to get that. So it's 484. And again, you can round whatever you like. This one rounds to 0, so I'll leave it off. Right? Now let's do one more. So P of 3 equals 350, 1.176 cubed. And again, so I'll clear. So I'll do 1.176 caret to the 3, and then times 350 to get 569. All right. And then again, you continue on and make the rest of your chart. And then these are your X and Y coordinates, like if you're plotting. So this is the coordinate on the vertical axis. This is your coordinate on the horizontal axis. And so just like I did to plot this point 244, I would just go to 2 on my chart, go up to 44, and I put a box just to differentiate them. But you can use a different color pencil or something too. Right. So does that make sense? Is that good? Any questions about plotting, sketching, function finding, modeling? No? All right. Awesome. And so, yeah, so ideally, what you'll have are 2 functions that kind of fit the data nice. So let me just show you. So let me kind of make a little mock picture here. So ideally, this is what you'd get. But population for Buffalo is not great, as I said. But ideally, you'll have something like this. So you have population like that. All right. This would be great, because then what you can do is, so again, this is the years, and this is population. If your function looks like, if your data looks like this, what you would do is you would just say, oh, for the first part, I want a vertical, or I want a line that goes through it. So I could take my pencil and be like, oh, this is a great fit. It's kind of close to these points up there. It's kind of close to these points down here. I'm going to put my line right there. Right? And that would be your line. Right? And then you would find the equation of the line like that. And then what you'd do is you'd average all of the relative growths, and you hopefully would find something like, oh, maybe it looks like that. And so ideally, your picture will look something like this, if not even better, if you choose good data, right? You kind of want data that has one trend or another trend, but not both. Like the Buffalo data, it goes up and then it goes down. It's not ideal. Any questions? This is what you Yeah?
I'm sorry.
No,
no, what was the calculation you used? You said 1.76 to find the.
Oh, that was that's I used, so this is 17.6% relative growth on average. So I use that for my relative growth for my model, for my exponential, but where I got that was I went to.
No, I understand that part.
Okay. Yeah.
It's just like how you got when you were doing the table and you got like 411.6. Well, you did something on your calculator that.
Oh, let me see.
Didn't understand.
So right here, yeah. So I did. Let me see if you can see this. There we go. I did 1.176.
Okay.
And then, so in this case, it's to the 1. So you could put that if you want. And then I multiplied it by 350.
Oh, okay.
Yeah. And you just proceed with the rest. So like I said, for the 3, for instance, you did 1.176, and then caret is exponentiation to the 3. I did enter, and then I multiplied that times 350 to get 569 and some change. And the only reason I do that is just sometimes calculators can be finicky, especially these kind of calculators can be a little picky on how you put things in them. So I like to do this part, the power first, and then multiply it times the 350 at the end. It just kind of prevents any errors from happening.
Okay, because I'm getting like a totally different number, and I'm doing exactly what you're doing.
Are you using you're using like a caret button?
Yeah.
Huh.
At 1.76 caret 1 times 350, and I got 616.
616.
Do you have the same calculator as him?
No. Hold on a second.
It's the wondering if it was in like degrees or like radians.
0.76.
It
Wait a
should-
minute. I think I might have jacked something up. 1.176 caret 1 times 350. Okay. Yeah, I know it was my fault. I
Okay.
totally screwed something up.
Oh,
Okay.
no worries. I know I don't like these calculators very much because I always screw things up with them as well. But as long as you're getting the right number, you're good to go then. All right. Any other questions with the computation? No? All right. So let me know if you have any issues with that. But let's see, there's more to this. Let me move this stuff over here. So the last part is just a bunch of kind of questions to analyze what you found. Again, it's kind of like if you took physics in high school, it kind of should remind you of that, the physics labs. But what does your exponential model say the population should be in 55, 85, and 15? And again, just like with the line, you're just plugging in the corresponding x value or t value for those years. So for 1955, again, 1955, the way we set it up, 1955 is 5.5 decades after 1900. So in my model here, I'm going to plug in t equals 5.5 because this t is in decades since 1900. All right. So whatever you're plugging in for t should be in those kind of units. So for
if
instance,
we used like the actual year, could we just plug in 19? I think it was 55 that you said.
yeah, if you do the, you have to be a little careful. So for the line, yes, but for the exponential model, you have to be a little careful because, where's my sheet? If you go back to the original chart in the beginning, all of these percent growths will be, or the relative growth rates will be in per decade. So if you just average these up like I was doing and use those for your R, your little r, your relative growth rate, then it's always going to be in per decade. Does that make sense?
No.
So like this is 20.2% growth per decade because we're doing it from, where we're computing the absolute growth in this entire decade and then dividing it by the population 1900. So this percent is in per decade. This percent, 19.6%, is that much, 19.6% per decade in this decade. So if you average these up, they're always going to be in some percent growth or decay per decade, not per year. If you want to do,
recommend us to use the 5.5 instead of the actual year.
yeah, at least for the exponential model, just because you're not going to be able to get relative growth rates per year, because to do that you would need population data every single year. If that makes sense.
Kind of. I'm sure I will probably have questions about it.
That's okay. I guess what you could do, yeah, I think you just want to do it per decade, at least for the exponential one. The line you can do either way because you're just kind of scaling things because it's linear. But for the data, you probably want to do it per decade. I guess you could divide your rate by 10. It's all kind of not very precise. We're just kind of playing around with models and trying to fit them to data. So you could see if that worked for you, like, you know what I mean? So divide it by 10. But I would keep it, just make things simpler. Yeah. But anyway, so for 55, you're going to do P of 5.5 because it's, so 1950. 5 is 5.5 decades after 1900. Right. And then you just plug it in. So I don't know what I get. I get 350 times 1.176 to the 5.5. Right? Maybe I'll do it in this calculator. So again, it's going to be, there we go, 1.176 caret 5.5. Some number. It took a oddly long time to do that. And then times 350. So you get something like that. So 8, 5, 4, say. And this is 1,000 people. Right? And obviously that's ridiculous. The population of Buffalo has never been that high. So the exponential model, as I said, will grow really fast. So it just isn't something that can be sustained. And then you would do the rest, right? So you do 1985 and 2015. Right. All right. So that, again, that's kind of just like the linear part. And then this question, how do the values from the linear and exponential models compare? Right. And again, there's not really right or wrong answer for these. And if we're looking just at my numbers here, the exponential is much higher. Much higher. Does not fit data. Doesn't really fit later data. I don't know, just something you just want to say, like, you know, in your case, the line might be really high and the exponential model might be in decay even. So like you would mention that the linear model, and if that was the case, the linear model was much higher, or you know, the exponential model was too low, or just, you want to just look at your data, you want to go to your table and you want to kind of analyze it and describe how these two models compare. Right? Nothing, there's no right or wrong answer. Just be like, oh, one's really low, one's really high, or maybe they both fit really well. And you just say, they both fit really well, right? Right? Can you find what the actual population was in 55, 85, and 2015? Why do they differ? This might not be easy. If you have a really big city, you might be able to find the population every single year. But most smaller cities only have population data available from the census. So if you can't find the population in your city, like the actual population in 55, 85, and 15, then don't worry about this. Just be like, I can't find the population data in those years. But this question, why do they differ? Basically, what we've constructed here are two models to approximate the data. And so they're always going to differ because in reality, populations don't grow linearly or exponentially. They have other factors, like I said in that first question. They have factors like World War II will influence their population. You know, sometimes people don't want to live in cities, or maybe there's some cities where there's huge booms and different outside forces that influence how populations grow. So models will never perfectly fit the data, right? So that's that. Again, just kind of ramble on a little bit. And the last question, which model best predicts the population of a city? Explain your reasoning. What might the limitations, sorry about that. What might the limitations of your model be? So this is kind of what I was just talking about a little bit in the previous problem. You want to first just look at your chart, see which model best fits. If this was your data, I would probably go with the line because, as I said, the exponential blows up. It's like you're like in New York City territory in like a few decades, and obviously Buffalo is nowhere near that size. So this is a horrible model because it goes up way too fast and it only hits these first few points really well. So the line kind of is best overall, maybe. But again, just say which one you think is best and why. And then what might the limitations be? As I said, both models won't be good in the long term because populations just don't grow forever in one model. Like you'll have a population like Buffalo, exponential growth in these first 4 decades. It's perfect, it perfectly fits this exponential curve, right? Like almost exactly for these first 4 decades, which is really good. Like you wouldn't almost expect to see that. But after that, it levels off and then it just declines. So it's kind of cool. It's almost like 3 models, right? In these first few decades, you have this exponential growth. In these next 3 decades or 2 decades, you have what is essentially linear growth, right? You can put a line through that pretty well. And then after that, you have exponential decay. So if you wanted to model this population, you could really divide it into 3 smaller models, each modeling some subsection of the years given. But that's besides the point. You just, so you just want to say like, oh, outside forces, you might have to use different models for different years. Things impact populations. Just kind of talk about it. What you think the limitations your model might be. If your city does exhibit exponential growth and you do have a beautiful curve, like if your population looks literally like that and you are blowing up exponentially, then you might say, oh, the limitations of my model, although it fits it perfectly right now, the population might, just like buffaloes, at some point level off, and then it might even decay. All right, but that's something you can talk about if that's what happens to your data. Any questions? So the only parts that really I'll be checking to make sure you did things correctly are, I'm gonna look at how you found the equation of your line. I'll be making sure that you found the slope and the y-intercept, that you gave me an actual equation, and then I'll be looking to make sure you kind of plug things in correctly, know how to use your model, and then I'll be looking down here to make sure you actually computed or gave me a valid exponential function, and that you plotted it correctly, and that everything kind of makes sense relative to what you gave me, right? Don't worry so much about answering like the word. Just kind of answer them, do the best you can for the word, like the question.